In this video, we will review the concept of linear approximations. In the graph in the upper right-hand corner of your screen is the graph of two functions, f of x, which is the square root of 25 minus x squared, and g of x, which is minus 3/4 times x minus 3 plus 4. So here the line is g of x. And we'd like to make some observations about these graphs. So we'll look at them in Desmos. What we can see is that the orange graph is tangent to the blue graph at the point 3-4. And if you zoom in around the point 3, 4, you will see that the graph of f of x, which is square root of 25 minus x squared, begins to look more linear. In fact, the graphs of f of x and g of x appear to be the same as you zoom in. And this is that local linearity property of differentiable functions, that if you zoom in on those functions near a point, they start to look linear. So what we can say is that for some small interval near the point, say 3, 4, the graph of f of x is approximately the same as the graph of g of x. So here we have that f of x is approximately equal to g of x near x equals 3. Well, how do we get that equation for the tangent line to f of x at x equals 3? Well, let's mark the point 3, 4 on here. Okay, and we're going to call that point, we'll call it a f of a. And we're going to look at points that are near f of a. So, for example, we want to look at the point here. We want to look at the point on the graph here. We're going to call this point x f of x. And we're going to approximate that point by this point here. And the question is what is the value of that point? Well, the distance between x and a is x minus a. And the slope of this line, if it's going to be the tangent line, is going to be f prime of a, because it's tangent to the graph of f of x at x equals a. And so the distance that you move from the point a f of a to this approximating point is going to be f prime of a, the slope, times x minus a. And that way you can think about the rise over run formula for slope, and the slope is clearly f prime of a times x minus a divided by x minus a. So here we're saying that this point right there is the point x, and then it is f of a plus f prime of a times x minus a. Here f prime of a is negative, and that is why we move down from f of a. This is called the linear approximation. So for x close to a, f of x we say is approximately f of a, some point a near x, plus f prime of a times x minus a. So in the case of our function f of x equals the square root of 25 minus x squared, we have that f of 3 is approximate or is equal to 4. And then f prime of 3, if you work out the derivative yourself, is equal to negative 3/4. So we say that f of x is approximately f of a, which is 4, plus a negative 3/4 for the slope times x minus 3. And so this is a good approximation for f of x for x near 3. Now that's the way that we can see how to come up with this linear approximation graphically. What about algebraically using the definition of the derivative? Okay, we know that f of x, or f prime of a, is equal to the limit as x goes to a of f of x minus f of a over x minus a. And so if f prime of a is equal to limit, we can say that the derivative is approximately just this difference quotient. If we multiply through by x minus a, we see that f prime of a times x minus a is approximately the same as f of x minus f of a. So we can say that f of x is approximately f of a plus f prime of a times x minus a. And that's an algebraic way to get at this linear approximation formula. Now, for the purposes of this lesson, we're actually going to call this linear approximation, or the local linearization of f of x, we're going to give it a name. We're going to call it L of x. So this formula we're going to call L of x. And L of x has two interesting properties that we want to focus on. Okay? Those properties are that L of a is equal to, well, it's f of a plus f prime of a times a minus a. But a minus a is, of course, 0. So L of a is equal to f of a. The derivative of L of a is going to be the derivative of this function. So the derivative is going to be 0 plus f prime of a is a constant, so the derivative of x minus a is 1. So this is plus f prime of a times 1, so that's equal to f prime of a. And so this linear approximation has the property that it matches the value of the function at x equals a and matches the derivative of the function at x equals a. We, of course, can see this graphically because here, for the function f of x, we see that f of x and g of x both have the same value at x equals a, but also they have the same derivative at x equals a because g of x is tangent to f of x. So these two properties are going to be our defining properties of an approximation to a function. We would like that the value of the function is equal to the value of the approximation, and that the value of the derivative is equal to the value of the derivative of the approximation. So let's look at two examples. The first example is we're going to look at the function e of x, e to the x. And what we would like to do is find the linear approximation of e to the x around x equals 0. So in this case, e to the x, our linear approximation, L of x, is going to be f of 0 plus f prime of 0 times x minus 0. Now, f of 0 is e to the 0. And then the derivative of e to the x, of course, is also e to the x. So f prime of 0 is also e to the 0. And that's multiplied by x minus 0. And so we get 1 plus 1 times x. So our linear approximation is the function 1 plus x. So I'm going to draw the function 1 plus x, which is going to be tangent to e to the x. So this is our function 1 plus x, and this is e to the x. Of course, it's tangent at x equals 0. And you can see that it's a good approximation of e to the x as long as you stay within a small range of e to the x. A small range of x equals 0, excuse me. Okay, so that's one example of a linear approximation. Okay, let's look at a second example. Let's look at the function f of x is equal to 1 minus e to the minus x. So here, f of 0 is 1 minus e to the 0, which of course is 1 minus 1, or 0. Now, the derivative of f of x is actually e to the minus x. So f prime of 0 is e to the 0, or 1. So the linear approximation in this case is going to be f of 0 plus f prime of 0 times x minus 0. And f of 0 is 0, f prime of 0 is 1, and that gets multiplied by x. So the function x is a linear approximation. So here I will draw a linear approximation that's tangent to e to the x. Notice that the value there is equal, plus the slope or the derivative is equal, where the line is tangent to 1 minus e to the minus x. And the linear approximation is a good approximation near, again, x equals 0. Let's look at a few notes about these linear approximations. We'll notice that if f of x, in this case, is concave down, then the linear approximation is going to be an overestimate. Notice that for that concave down function, the approximating line is above the concave function. We could also draw a different concave down function, and of course, if we drew the tangent line, it would be above. So using similar logic, right, if f of x is concave up, then the linear approximation is an underestimate. So let's look at this example. Here we can see that the linear approximation of e to the x is an underestimate, and e to the x is concave